In probability theory, the normal distribution is a very common continuous probability distribution. Normal distributions are important in statistics and are often used in the natural and social sciences to represent real-valued random variables, whose distributions are not known. The normal distribution is useful because of the central limit theorem. In its most general form, under some conditions, it states that averages of random variables independently drawn from independent distributions converge in distribution to the normal, that is, become normally distributed when the number of random variables is sufficiently large. Physical quantities that are expected to be the sum of many independent processes often have distributions that are nearly normal. Moreover, many results and methods can be derived analytically in explicit form when the relevant variables are normally distributed. The normal distribution is sometimes informally called the bell curve. However, many other distributions are bell-shaped. The terms Gaussian function and Gaussian bell curve are also ambiguous because they sometimes refer to multiples of the normal distribution that cannot be directly interpreted in terms of probabilities. The probability density of the normal distribution is the mean or expectation of the distribution. The parameter is its standard deviation with its variance. Then, a random variable with a Gaussian distribution is said to be normally distributed and is called a normal deviate. If the distribution is called the standard normal distribution or the unit normal distribution denoted by a random variable with that distribution, is a standard normal deviate. The normal distribution is the only absolutely continuous distribution whose cumulants beyond the first two are zero. It is also the continuous distribution with the maximum entropy for a specified mean and variance. The normal distribution is a subclass of the elliptical distributions. The normal distribution is symmetric about its mean, and is non-zero over the entire real line. As such, it may not be a suitable model for variables that are inherently positive or strongly skewed, such as the weight of a person or the price of a share. Such variables may be better described by other distributions, such as the log normal distribution or the Pareto distribution. The value of the normal distribution is practically zero when the value x lies more than a few standard deviations away from the mean. Therefore, it may not be an appropriate model when one expects a significant fraction of outliers, values that lie many standard deviations away from the mean, and least squares and other statistical inference methods that are optimal for normally distributed variables often become highly unreliable when applied to such data. In those cases, a more heavy-tailed distribution should be assumed and the appropriate robust statistical inference methods applied. The Gaussian distribution belongs to the family of stable distributions, which are the attractors of sums of independent, identically distributed distributions whether or not the mean or variance is finite. Except for the Gaussian, which is a limiting case, all stable distributions have heavy tails and infinite variance. It is one of the few distributions that are stable and that have probability density functions that can be expressed analytically. The others being the Cauchy distribution and the Elie-Acute Vy distribution. Definition: standard normal distribution. The simplest case of a normal distribution is known as the standard normal distribution. This is a special case when mu equals 0 and sigma equals 1, and it is described by this probability density function. The factor in this expression ensures that the total area under the curve is equal to 1. The 1/2 in the exponent ensures that the distribution has unit variance. This function is symmetric around x equals 0, where it attains its maximum value, and has inflection points at +1 and -1. Authors may differ also on which normal distribution should be called the standard one. Gauss defined the standard normal as having variance, that is, Stigler goes even further, defining the standard normal with variance. General normal distribution. Every normal distribution is a version of the standard normal distribution whose domain has been stretched by a factor sigma, and then translated by mu. the probability density must be scaled by so that the integral is still 1. If z is a standard normal deviate, then x equals z sigma plus mu will have a normal distribution with expected value mu and standard deviation sigma. Conversely, if x is a general normal deviate, then z equals sigma will have a standard normal distribution. Every normal distribution is the exponential of a quadratic function, where a is negative and c is. In this form, the mean value mu is minus b, and the variance sigma 2 is minus 1. For the standard normal distribution, a is minus 1/2, b is 0, and c is. Notation: the standard Gaussian distribution is often denoted with the Greek letter. The alternative form of the Greek phi letter, phi, is also used quite often. The normal distribution is also often denoted by n. Thus, when a random variable x is distributed normally with mean mu and variance sigma 2, we write alternative parameterizations. Some authors advocate using the precision as the parameter defining the width of the distribution, instead of the deviation sigma or the variance sigma 2. The precision is normally defined as the reciprocal of the variance, 1, sigma 2. The formula for the distribution then becomes: this choice is claimed to have advantages in numerical computations when sigma is very close to 0 in simplified formulas in some contexts, such as in the Bayesian inference of variables with multivariate normal distribution. Also, the reciprocal of the standard deviation might be defined as the precision, and the expression of the normal distribution becomes according to Stigler. This formulation is advantageous because of a much simpler and easier to remember formula, the fact that the PDF has unit height at 0, and simple approximate formulas for the quantiles of the distribution. Properties, symmetries and derivatives. The normal distribution f, with any mean mu and any positive deviation sigma, has the following properties. It is symmetric around the point x equals mu, which is at the same time the mode, the median and the mean of the distribution, and it divides the data in half. It is unimodal. Its first derivative is positive for x less than mu, negative for ex greater than mu, and 0 only at x equals mu. The area under the curve and over the x-axis is unity. Its density has two inflection points, located one standard deviation away from the mean, namely at x equals mu minus sigma and x equals mu plus sigma. Its density is log concave. Its density is infinitely differentiable, indeed supersmooth of order 2. Its second derivative f is equal to its derivative with respect to its variance sigma 2. Furthermore, the density of the standard normal distribution also has the following properties. Its first derivative is minus x. Its second derivative is, more generally, its nth derivative is nhn, where hn is the Hermite polynomial of order n. It satisfies the differential equation. Or if we want to calculate the probability of a normally distributed variable x with known m, then we can calculate it by standard normal distribution, equivalent to using probability table. Moments. The plane and absolute moments of a variable x are the expected values of xp and xp, respectively. If the expected value mu of x is 0, these parameters are called central moments. Usually we are interested only in moments with integer order p. If x has a normal distribution, these moments exist in a finite for any p whose real part is greater than -1. For any non-negative integer p, the plane central moments are here n. Denotes the double factorial, that is, the product of every number from n to 1 that has the same parity as n. The central absolute moments coincide with plane moments for all even orders, but are non-zero for odd orders. For any non-negative integer p, the last formula is valid also for any non-integer p greater than -1. When the mean mu is not 0, the plane and absolute moments can be expressed in terms of confluent hypergeometric functions 1f1 and u. These expressions remain valid even if p is not integer. See also generalized Hermite polynomials. The expectation of x conditioned on the event that x lies in an interval a, b, is given by where f and f respectively are the density and the cumulative distribution function of x. Fourier transform and characteristic function. The Fourier transform of a normal distribution f with mean mu and deviation sigma is where I is the imaginary unit. If the mean mu is 0, the first factor is 1, and the Fourier transform is also a normal distribution on the frequency domain, with mean 0 and standard deviation 1, sigma. In particular, the standard normal distribution is an eigenfunction of the Fourier transform. In probability theory, the Fourier transform of the probability distribution of a real-valued random variable x is called the characteristic function of that variable, and can be defined as the expected value of atx, as a function of the real variable t. This definition can be analytically extended to a complex value parameter t. Moment and cumulant generating functions. The moment generating function of a real random variable x is the expected value of etx, as a function of the real parameter t. For a normal distribution with mean mu and deviation sigma, the moment generating function exists and is equal to the cumulant generating function is the logarithm of the moment generating function. Namely, since this is a quadratic polynomial in T, only the first two cumulants are non-zero, namely the mean mu and the variance sigma 2. Cumulative distribution function. The cumulative distribution function of the standard normal distribution, usually denoted with the capital Greek letter, is the integral. In statistics, one often uses the related error function, or f, defined as the probability of a random variable with normal distribution of mean 0 and variance 1/2 falling in the range. That is, these integrals cannot be expressed in terms of elementary functions, and are often said to be special functions. However, many numerical approximations are known. See below. The two functions are closely related, namely for a generic normal distribution f with mean mu and deviation sigma. The cumulative distribution function is the complement of the standard normal CDF, is often called the Q function, especially in engineering texts. It gives the probability that the value of a standard normal random variable x will exceed x. Other definitions of the Q function, all of which are simple transformations of, are also used occasionally. The graph of the standard normal CDF has twofold rotational symmetry around the point, that is, its antiderivative is. The cumulative distribution function of the standard normal distribution can be expanded by integration by parts into a series, where denotes the double factorial. As an example, the following Pascal function approximates the CDF function CDF extended var value sum extended I integer begin sum equals x value equals x for I equals 1 to 100 do begin value smiley face sum equals sum plus value end result equals 0.5 plus asterisk exp 2 end standard deviation and tolerance intervals. About 68% of values drawn from a normal distribution are within one standard deviation sigma away from the mean. About 95% of the values lie within two standard deviations, and about 99.7% are within three standard deviations. This fact is known as the 68 to 95 minus 99.7 rule, or the 3 sigma rule. More precisely, the probability that a normal deviate lies in the range mu minus n sigma and mu plus n sigma is given by to 12 decimal places, the values for n equals 1, 2, 6 are. Quantile function. The quantile function of a distribution is the inverse of the cumulative distribution function. For a normal random variable with mean mu and variance sigma 2, the quantile function is the quantile of the standard normal distribution is commonly denoted as ZP. These values are used in hypothesis testing, construction of confidence intervals and QQ plots. A normal random variable x will exceed mu plus sigma zp with probability 1 minus p, and will lie outside the interval mu plus or minus sigma zp with probability 2. In particular, the quantile z0.975 is 1.96, therefore a normal random variable will lie outside the interval mu plus or minus 1.96 sigma in only 5% of cases. The following table gives the multiple n of sigma such that x will lie in the range mu plus or minus n sigma with a specified probability p. These values are useful to determine tolerance interval for sample averages and other statistical estimators with normal distributions. Zero variance limit. In the limit when sigma tends to 0, the probability density f eventually tends to 0 at any x mu, but grows without limit if x equals mu, while its integral remains equal to 1. Therefore, the normal distribution cannot be defined as an ordinary function when sigma equals 0. However, one can define the normal distribution with zero variance as a generalized function, specifically, as Dirac's delta function, delta translated by the mean mu, that is f equals delta. Its CDF is then the Heaviside step function translated by the mean mu, namely central limit theorem. The central limit theorem states that under certain conditions, the sum of many random variables will have an approximately normal distribution. More specifically, where x1, xn are independent and identically distributed random variables with the same arbitrary distribution, 0 mean, and variance sigma 2, and z is their mean scaled by then, as n increases. The probability distribution of z will tend to the normal distribution with 0 mean and variance sigma 2. The theorem can be extended to variables xi that are not independent and, or not identically distributed if certain constraints are placed on the degree of dependence and the moments of the distributions. Many test statistics, scores, and estimators encountered in practice contain sums of certain random variables in them, and even more estimators can be represented as sums of random variables through the use of influence functions. The central limit theorem implies that those statistical parameters will have asymptotically normal distributions. The central limit theorem also implies that certain distributions can be approximated by the normal distribution. For example, the binomial distribution B is approximately normal with mean NP and variance NP for large N and for P not too close to 0 or 1. The Poisson distribution with parameter lambda is approximately normal with mean lambda and variance lambda for large values of lambda. The chi-squared distribution chi2 is approximately normal with mean k and variance 2k for large k. The student's t distribution T is approximately normal with mean 0 and variance 1 when nu is large. Whether these approximations are sufficiently accurate depends on the purpose for which they are needed, and the rate of convergence to the normal distribution. It is typically the case that such approximations are less accurate in the tails of the distribution. A general upper bound for the approximation error in the central limit theorem is given by the Berry-Esseen theorem. Improvements of the approximation are given by the Edgeworth expansions. Maximum entropy of all probability distributions over the rails with a specified mean mu and variance sigma 2, the normal distribution n is the one with maximum entropy. If x is a continuous random variable with probability density f, then the entropy of x is defined as where f log f is understood to be 0 whenever f equals 0. This functional can be maximized, subject to the constraints that the distribution is properly normalized and has a specified variance. By using variational calculus, a function with two Lagrangian multipliers is defined, where f is, for now, regarded as some function with mean mu and standard deviation. At maximum entropy, a small variation delta f about f will produce a variation delta L about L which is equal to 0. Since this must hold for any small delta f, the term in brackets must be 0, and solving for f yields Using the constraint equations to solve for lambda 0 and lambda yields the normal distribution. Operations on normal deviates. The family of normal distributions is closed under linear transformations. If X is normally distributed with mean mu and standard deviation sigma, then the variable y equals x plus b for any real numbers a and b is also normally distributed with mean a mu plus b and standard deviation a sigma. Also, if x1 and x2 are two independent normal random variables with means mu1, mu2 and standard deviations sigma 1, sigma 2, then their sum x1 plus x2 will also be normally distributed, proof, with mean mu1 plus mu2 and variance. In particular, if x and y are independent normal deviates with zero mean and variance sigma 2, then x plus y and x minus y are also independent and normally distributed with zero mean and variance 2 sigma 2. This is a special case of the polarization identity. Also, if x1, x2 are two independent normal deviates with mean mu and deviation sigma, and e, b are arbitrary real numbers, then the variable is also normally distributed with mean mu and deviation sigma. It follows that the normal distribution is stable. More generally, any linear combination of independent normal deviates is a normal deviate. Infinite divisibility and Cramer's theorem for any positive integer n. Any normal distribution with mean mu and variance sigma 2 is the distribution of the sum of n independent normal deviates, each with mean mu, n and variance sigma 2, n. This property is called infinite divisibility. Conversely, if x1 and x2 are independent random variables and their sum x1 plus x2 has a normal distribution, then both x1 and x2 must be normal deviates. This result is known as Cramer's decomposition theorem, and is equivalent to saying that the convolution of two distributions is normal if and only if both are normal. Cramer's theorem implies that a linear combination of independent non-Gaussian variables will never have an exactly normal distribution, although it may approach it arbitrarily closely. Bernstein's theorem states that if x and y are independent and x plus y and x minus y are also independent, then both x and y must necessarily have normal distributions. More generally, if x1, xn are independent random variables, then two distinct linear combinations akxk and bkxk will be independent if and only if all xk s are normal and akbk sigma 2k equals 0, where sigma 2k denotes the variance of xk.